In April 2020, astronomers thought they were watching a comet from another star system fall apart. They knew the script, but the fragments didn't dissolve like crumbs in water. Instead, they held together, almost as though parts still had an inner grip. This unprecedented behavior sparked a debate at NASA's, not about rewriting physics, but about how to interpret the strange data. It was a clear reminder of how science moves forward, through testing, questioning, and refining. In April 2020, astronomers thought they were watching yet another comet fall apart. But 3IATLAS didn't follow the script. The images suggested something both familiar and unexpected, splitting experts into different camps almost overnight. Imagine tracking a visitor from another star system, only to discover it won't behave as you predict. That's the puzzle that sparked NASA's ongoing debate, and it's worth slowing down to see what the evidence really says. First, images and the surprising behavior. Comets are usually predictable in one way. When they break apart, the process looks familiar no matter which object you watch. Cracks form, small pieces split off, and the gas and dust spread out in a faint cloud as the nucleus, the solid center, loses its strength. That's been true for sun grazers that disintegrated quickly near the sun, and for long-period comets that disassembled slowly in deep space. Yet when astronomers trained their telescopes on 3IATLAS, expecting the same pattern, the fragments did not behave on schedule. Instead of dissolving like crumbs in water, parts of this interstellar comet continued holding together long after the first signs of stress were visible. The earliest observations came from a combination of Hubble images and ground-based telescope data. At first, the pictures showed something familiar, faint streaks and dimming brightness that hinted at fractures in the main body. That alone was not unusual. Comets are fragile structures made of dust, rock, and frozen gas that can give way as they heat up. The expectation was simple, like watching a snowball soften in the sun until the outer shell falls apart and the core rapidly follows. The initial bright core of Atlas appeared to be breaking, which seemed to set up the standard script of disintegration. But then, the cracks did not finish the job. Several distinct clumps showed up in images over time, and instead of quickly dispersing into a diffuse cloud as standard models suggested, these clumps looked surprisingly stable. Observers noticed them maintaining coherence much longer than anticipated, almost as though parts of the weakened comet still had an inner grip holding them together. This was the turning point, because the ordinary storyline of cometary breakup could no longer explain what was unfolding in the data. To understand why it was puzzling, it helps to know what normally drives the process. A typical comet nucleus is only loosely bound. It is a mixture of frozen material like water ice and carbon dioxide ice, along with dust and rocky grains. As sunlight heats the black surface, the ices start turning directly into vapor, a process called sublimation. That steady release of gas undermines the comet's structural support. When stresses grow strong enough, chunks of the nucleus lose cohesion. They drift apart, surrounded by the dusty coma, until the fragments dissolve into the background of space. With Comet Eisen in 2013, for example, the nucleus came apart so quickly near the Sun that only a thin streak of debris remained. Researchers expected something similar for Atlas, especially given its smaller size and fragility. What made Atlas different was its origin. This was only the second confirmed visitor from outside our solar system, earning the official designation 3I. An interstellar comet is simply a comet not bound to the Sun, moving on a trajectory that passes through once and leaves. Because of its higher speed compared with local comets, 3IATLAS was a rare opportunity to study material that formed around another star system. Very few chances exist to capture such objects, let alone during active fragmentation, which added extra pressure to interpret each observation carefully. A useful way to picture it is with the snowball analogy again. Most of the time, once cracks appear in a snowball, the rest soon collapses. With Atlas, it was as if shards of the snowball were still packed tight, refusing to crumble even after the surface showed damage. Teams using Hubble reported seeing discrete pieces lined up along the comet's motion, resembling beads rather than loose powder. That resilience drew comparisons within NASA's community. Earlier comets like Ison, or smaller periodic comets typically had no resistance once fracturing began. ATLAS seemed to stall the process. Some observers even pointed out that the strongest fragments maintained brightness across several days, which placed them apart from the fast-fading remnants of most breakups. These images, instead of confirming a clear breakup, complicated the story. Rather than a simple end, they suggested that the mechanics of fragmentation might vary more than previously believed, and that interstellar comets could bring unexpected twists. The immediate result was not a new law of physics, but a pressing question of how best to interpret limited and sometimes ambiguous data. What scientists really mean by a debate. When the word debate appeared in stories about 3IATLAS, many people pictured NASA teams split over the basic rules of the universe. That image of scientists locked in conflict can be dramatic, but it is not what happened. In research fields like comet science, debate does not mean that physics itself is being contested. Instead, it usually describes disagreements about how to read data that is limited or ambiguous. The laws of gravity, orbital mechanics, and thermodynamics were not up for negotiation here. What was under discussion was how to explain the strange set of images and measurements gathered during the breakup of 3IATLAS. The key uncertainties centered around the fragments themselves. When the initial crack appeared and pieces separated, astronomers expected them to drift apart in a way consistent with the weak structure of comet nuclei. A nucleus is the solid heart of a comet, but its mechanical strength is extremely low compared to rock or even packed ice on Earth. These objects are more fragile than they look, more like loosely bonded snow than a solid boulder. Once fractured, traditional comets scatter their fragments relatively quickly. Yet, in this case, the question arose: did the detached pieces of 3IATLAS stay loosely held together by their own tiny gravitational pull, or did they only seem coherent because of the way telescopes were capturing their light? This uncertainty opened the door to multiple explanations, and, with it, the sense of a debate. One working hypothesis suggested that the clumps were more cohesive than expected. Perhaps the material strength of this interstellar object was stronger than typical solar system comets, giving the illusion of resilience. Another hypothesis pointed toward viewing geometry. The angle from which telescopes saw the fragments could have created the appearance of stability, when in reality they might already have been drifting apart. Both ideas remained linked to well-known comet physics, but emphasized different interpretations of the limited images. The role of sublimation also entered the conversation. Sublimation happens when solid ice turns directly into gas, which is the normal driver of comet activity near the Sun. For ATLAS, some astronomers speculated that unusual patterns of sublimation could have delayed or altered the way fragments separated, making them appear more drawn out over time. Others argued that simple differences in observing conditions between NASA's Hubble telescope and ground-based facilities could explain why stability seemed more dramatic in some datasets than others. This variety of interpretations led to different reconstructions of the breakup sequence. Several research teams, often working with the same raw images, produced graphics or models that disagreed in details such as how many fragments survived for days, or how fast they spread apart. None of these reconstructions challenged the idea that solar heating and internal weakness drove the breakup. What they reflected was the inevitable difficulty of piecing together events from snapshots of a fast-moving, distant object. Public attention grew when words like unprecedented appeared in press releases. For many readers, that term implied a true crisis in physics rather than a technical discussion about fragmentation timing or geometry. Scientists, however, were clear that they were still working within the same framework of known comet behavior. The term unprecedented only meant that the exact observed pattern had not been documented before, not that the foundations of astrophysics were under threat. The central takeaway is that this NASA debate was about mechanism and nuance, not about rewriting fundamental science. Competing interpretations are a normal part of research. Rather than signaling confusion, they highlight a healthy process. Multiple teams testing different hypotheses against a shared pool of evidence. When surprises show up in the data, those surprises force researchers to check assumptions and refine models. That is science functioning as intended. For anyone following space discoveries, The situation offers a useful lesson. The appearance of scientific conflict in headlines does not always mean that the basic rules of nature are disputed. Often, it is about specialists comparing notes on details that remain unclear. Keeping that in mind helps us read space news with sharper judgment, distinguishing between observations, interpretations, and hypotheses instead of blending them together. Conclusion: 3IATLAS was not a defiance of cosmic order, but a clear reminder of how science moves forward through testing, questioning, and refining. The fragments that seemed stubbornly stable showed researchers the limits of current models and the need to revisit assumptions with new data. That is the real story. Progress through careful disagreement. When space discoveries make headlines, it helps to separate fact from speculation. Ask yourself, what exactly was observed? What did scientists conclude from it? And what remains a working hypothesis? Staying curious while making these distinctions gives a steadier, clearer view of the universe.